Okay, I want to talk a little bit about water supplies, pumps, how they work, the different kinds of pumps to help understand things you might be looking at and what you have in your field. First of all, we work with multiple sources of water. We're working with wells, ponds, rivers, lagoons, so all kinds of water sources. We've got different pumps for different applications. In the picture here, we've got a floating pump. This is what we use typically for most ponds, lagoons, rivers. If we have deep enough water, we'll use a floating pump. This particular one is short coupled to a centrifugal pump. So we've got an electric motor short coupled to an electric pump. The nice thing about this is it self-primes. So there's other options out there where you put the pump and the motor up on the shore and you have a screen down in the river and you have to prime that every time you want to start it. And that is probably one of the biggest headaches for that type of pump is priming. So we do everything we can to eliminate priming issues. So we use a lot of these floating pumps. This is, like I said, this is a centrifugal floating pump. We can also do a line shaft, what they call a short set pump with floating as well. If we're needing higher pressure and sometimes higher flows, we'll go with a line shaft on a floating setup like this. Great setup. All of these options are going to be three-phase, typically 480 volts. So if you have single phase coming in, we're going to have to convert that to three-phase either through a rotophase or preferably a VFD. A VFD is a variable frequency drive that controls the speed of the electric motor and adjusts it to maintain the optimum pressure in the system. So think of a VFD as a throttle on your tractor. You speed it up and you slow it down based on what your load is. So it makes the motors very efficient. It makes it so they start slow. So when a three-phase motor starts with a VFD, it starts at 0 RPMs and it slowly speeds up to full speed, whatever that is, either 1700 or 3400. So it's easier on motor life because it doesn't just bam start and try to go to 3400 RPMs really fast, which can be hard on motors. VFDs are great for motor life. They're highly efficient. They're easy on the system. We don't have to worry near as much about water hammer. As we open and close valves in the system or as we flush filters, those VFDs can speed up and slow down those pumps to give us a lot of flexibility on how much water we're using at one time and maintain that set pressure that we want for our system. So a VFD can work with any of these pumps. All of these are electric. They're all going to be three-phase 480. The other thing to note on three-phase 480 is that if you switch two of the legs, you're going to switch the rotation. And all of these are very rotation specific. And so if you have two legs switched, so on initial startup, we're always checking that. But let's say the power company comes out and does some work, or you have an electrician come out and switch some components out, and two of the legs get switched, there's a possibility that the pump will be spinning in reverse. You'll get water, but you won't get much pressure. And so a lot of times if we're fighting something like that, we'll look at the rotation and make sure it's correct. Okay, second style of pump we'll talk about is the submersible. So this is what you'll see on top of the hole if you have a submersible. All you're going to see is an elbow coming up out of the ground, some kind of a wire leading into the ground, so there's almost nothing on top. But what's down in the hole is the submersible pump. And these can be large and they can be deep. We have a lot of deep wells in southern Missouri, 1,200 foot deep. We're pumping 1,000, 1,100 gallon a minute out with these submersible pumps. The advantage is they're typically less expensive than a line shaft, which we're going to get to next. These are the line shaft options. But the disadvantage is your electric motor is 1,000 foot in the ground. So if you need to service that, if something is going wrong electrically, let's say you get a lightning strike and something shorts out, now you've got to have someone come out and pull out 1,000 foot of well column, which is an expensive service call. There's advantages and disadvantages to both. We probably work 60% with submersibles and 30% with line shaft and 10% with some kind of a centrifugal. Submersible is probably the most common one we see. The other things to know on a submersible is there's different, your electric motor is down here on the bottom half of this, so it's down in the cool water, so you don't have to worry about cooling, so that they're self-cooled. The pump portion of it's on the top here, but again, that electric motor is down in the bottom of the hole if it does need to be serviced. And then the third option here is the line shaft. So we've got, this is an image that you'll see where the electric motor is basically attached to a shaft that goes down and it drives the bowls or the impeller that's down in the hole. Depending on how deep your water is, how much pressure you need will depend how many bowls there are. So if you need higher pressure, they simply stack more bowls on top of each other. Every one of those bowls basically boosts the pressure to the next bowl, and it builds pressure. So these are super good pumps. They last a long time. This is probably the most common thing we see in Nebraska and western Kansas are the line shaft pumps. There's two different kinds of lubrication for a line shaft pump. There's either water lube or oil lube. If you have an oil lube system, you'll have a little oil tank, a little 5-gallon or 3-gallon oil reservoir that sits off to the side of that, and you need to make sure you keep that charged with the proper lubricating oil, because what it's doing is it's oil lubricating that bearing, and if that starts to run dry without oil, it'll ruin that bearing pretty quickly, and you'll have an expensive service call on your hands. So make sure that if you have an oil lube, you're keeping those lubed up. Otherwise, the water lube is more common, but it slobbers water all the time, so it makes a little bit of a mess around your wellhead. So those are the three common pump types that we see. We work with all of them. We typically ask the well driller to service and supply line shaft and submersible. If you're looking for a floating pump option, a lot of times those are coming from NutraDrip. We do have some expertise related to supplying and servicing the other two types as well, depending on your location. So lots of options for pumping water, and we can usually figure out how to make it go. Okay, so this is an example of a line shaft pump in a wet well. So here we've got a reservoir we built. We've got a casing that goes down in the ground about 25 feet. Got that line shaft pump going down. This particular pump unit is a water lube. So you can see there's, like I mentioned earlier, there's going to be a little bit of water that always slobbers a little bit there around the pump to keep it lubricated. If it was an oil lube, you'd have an external reservoir, and that water or that oil would be dripping in on top of that bearing all the time. So this is a preferred method for taking water out of a reservoir. There's actually a stinger that goes out in the pond, and it's sucking water off the top of the pond. The cleanest water is always at the top of a reservoir, and so anytime we can get that surface water, it's going to be cleaner than pulling water off the bottom of a reservoir. Okay, another important thing to know about pumps is every pump has what's called a curve that has been calculated for it. You can request it from your pump supplier. It's a very important piece of information to know about how pumps work. So I've printed off a sample one here just to go over the basics of it. Let's focus on the center graph here first. So basically on the left-hand side, we've got feet of head. So feet of head is the pump language for pressure. So most people know about pressure and PSI. It's a direct calculation to convert feet of head to pressure. There's 2.3 feet of head in every 1 PSI. So if we had a graph here that went all the way to 230 feet of head, that pump would be able to produce 100 pounds of pressure. So that's what feet of head means. It's basically how far out of the ground or how far from static pumping level that pump is going to push water. Across the bottom, we've got flow. So you can see that this pump can perform anywhere from 0 gallons per minute all the way up to 1,600 gallons per minute. So we've got a huge range, and it can do that at this big range of pressure or head. So you can see here at, if we figured 10 PSI, which would be 23 feet of head, we would be pumping around 25 gallon a minute. Now if we go all the way up here to peak efficiency, and the efficiency curve is right on this side over here on the right hand side, we've got efficiency. So 80% efficiency is usually what we're shooting for. So you can see that anywhere above this line right here, this is this pump's sweet spot. It likes to operate right in here. That's where it's going to be the most efficient to convert that energy of power into pressure in the field. So if we're anywhere from 1,000 gallon a minute to 1,600 gallon a minute, that's the sweet spot for this pump to operate. Now you'll notice that they put a little mark right here. So this is, every pump has its designed operating capacity. This is what that particular pump has been designed for. And so the other line on here then that we need to pay attention to is how much power it requires. So you can see that at 1,000 gallon a minute, this pump is going to require 27 horsepower. If we go up to 1,600 gallon a minute, and we're basically at the same pressure, now we need another basically three horsepower to give us that flow and pressure. So a lot of numbers on here, but you can see the difference in like how a pump is going to operate. This is what I would call a fairly flat pump curve. In other words, once it gets up in here, it's pretty flat. There are some pump curves that are steeper. This is probably off of a centrifugal. If it was a submersible or a line shaft, it's probably going to be a little steeper than this. And why that's important is because if we need more pressure, we're going to use a different style of pump. Down here on the bottom, this is representing the net suction that the pump has been designed for. So there's also a suction factor. So if we're working with a pump that has negative head pressure, in other words, it's not sitting in the water, it's not down in a well, maybe it's trying to pull water up out of a reservoir or up out of a creek, it's going to have some negative suction. And so that's what this bottom graph down here represents. So a lot of information that goes into the pump curve. When you have a VFD, the VFD is a moving point. Like, it doesn't have a set RPMs and a set point that it's always going to pump at. That's going to change based on where that drive is throttling it up at. So to really understand how a VFD impacts it, you have to print out multiple pump curves and look at where the peak efficiency is, but that VFD should be able to achieve that at all times. The other thing I want to note on pumps is one of the things that kills pumps is cavitation. Especially on systems that have a suction on them, if there's any kind of an air leak where air can get into that suction side of the pump, it's going to cavitate, it's going to pull in little air bubbles, and those little air bubbles, when they get inside that pump and there's a vacuum, they explode. And it's like having a sandblaster inside your pump, and it will literally eat the inside of that pump if there's any kind of air that's getting in on that suction side. So it's very important, especially if you have a centrifugal that's pulling back, or that's pulling a suction to get water into the pump, that you maintain the suction side of that thing and make sure it's not getting little air bubbles in there, because that can damage a pump very quickly. Those are some of the basics of how pump curves work and what they mean and how to read them.